In this video, we are going to discuss about the properties of conditional probability. Okay, now there are three major properties. I would say three important ones. Okay, based on those three of sub properties, which we'll look into it as we start solving problems. Now, the first property talks about if you have an event and a sample space, what is the relation between them? Okay, like suppose say S is a sample space. Okay, S is sample space. Say A is an event. Alright, A is an event. Then the property says that P of S given A is the same as P of A given A, and this value is equal to 1. Okay, we need to prove this one, that this is equal to 1. Very simple proof. Very, very simple. What is the definition of conditional probability? That is, if you have P of A given B, then it is P of A intersection B divided by P of B. This is a given definition, correct? So when we say P of S given A, then we'll be writing this as, so P of S given A. So this is going to be P of S intersection A divided by P of A. See, S intersection A is nothing but A itself, correct? Sample space. So P of A divided by P of A, which is 1. The second one, that is P of A given A. So this is going to be P of A intersection A divided by P of A. See, when we have A intersection A, isn't it A itself? So we can write this as P of A divided by P of A, which is 1. This is the first property. Alright, now we'll move on to the second one. Okay, second property. See, the second property talks about the union of sets in this conditional probability case. That means if you have P of A union B given F, F being some event. Okay, so this is nothing but P of A given F plus P of B given F minus P of A intersection B given F. This we need to prove it. And the proof is quite easy, I would say. Okay, it's very, very simple. Okay, see, to start with this particular proof, first what we'll do, we'll again look at the basic condition. That is P of A given B is nothing but P of A intersection B by P of B, correct? Isn't it? So in place of A, what do we have here? That is, in place of A, we have A union B, right? And in place of B, we have this F. F is another event. So in place of this A, what do we write? A union B. And in place of B, what do we write? F. So what we are going to get is P of A union B intersection F divided by P of F. Isn't it? So this is what we are going to get. Now, take the normal law, distributive law. You are going to get this as P of A intersection B union P of B intersection F divided by P of F. Now we'll do distributive property of union over intersection. Okay, so just like whatever we have done. So if you do that, then we are going to get this as P of A intersection F plus P of B intersection F minus P of A intersection B intersection F whole over P of F, correct? So I might as well do individually P of F, P of F, P of F, correct? Now what is P of A intersection F divided by P of F? That's the definition, no? P of A given F. So in this case, we are going to get P of A union B given F is equal to P of A given F plus P of, sorry, plus P of B given F minus P of A intersection B given F. So this is going to be the second property. Now using the second property, we can get one more. What if A and B are disjoint sets? See, if A and B are disjoint sets, then the intersection would be 0, correct? Intersection has to be 0 because they're disjoint sets. Like the set and its complement, like A and A complement, there are no common numbers. That means they're disjoint sets, isn't it? So if A and B are disjoint, like in the second property, then the last one, that is P of A intersection B given F, that parameter would become 0, correct? So for disjoint, how the property is going to be, let's look into that one. For disjoint sets, A intersection B is 0, that is n of A intersection B would be 0, correct? Or phi P of A intersection A would be 0, you can call it however you want. So P of A union B given F would become P of A given F plus P of B given F. This is going to be the answer. Not answer, it's more like a property. Fair enough? So we are going to make use of this one and we are going to do the third property now. Alright? See, third property is P of E complement given F is equal to 1 minus P of E given F. Where of course you guys know the meaning of complement. So we have to prove this one. Very, very simple proof. Very, very direct. Okay. So what we are going to do is we are going to make use of that P of E and P of E complement. That is, we know that E union E complement is going to be S. S being the sample space, correct? That's a very known thing. So when you take P of E union E complement given F, this will be nothing but P of S given F, correct? Now E and E complement, they are disjoint sets, correct? Since they're disjoint sets, the intersection would be 0. That means here, what do we get? P of E given F plus P of E complement given F. This is equal to 1. Isn't that the first property? P of S given A or P of S given F, whatever that event. So what we are looking at is this is from the first property and the disjoint part is going to be from the second property, isn't it? So what do we have here? P of E complement given F is equal to 1 minus P of E given F. See, this is the proof. This is the proof for the third property. Fine. So 3 properties, very easy ones. Now, these properties are used in almost every problem. Okay, every problem we are going to use the same thing and different corollaries of these properties. Fair enough? So in the next video, we'll look into the problems based on conditional probability.